Hello and welcome. This is part 3 of the electricity and magnetism video series. Today I'm going to talk about electric potential and electric potential energy. So we're going to use energy concepts which we are familiar from mechanics. Very similar to gravitational potential energy. If you remember that topic, where you consider the change in the potential energy of an object when you lift it or bring it down from a height. Okay, so you basically have this object with mass m, therefore its weight is mg, and then you let it fall, basically. When it's free falling, you record the position. Initially it was at this point, let's say yi, and then a time later it is at yf. Okay, so it's going to speed up and all that, but just consider the work done by gravity. Now, work is when the force is a constant, basically force times distance, right? You are familiar with that idea. And in this case, both the force and displacement are vectors which point downward. The angle between them is 0. So it's simply a simple multiplication. So the distance traveled is what? Yi minus yf, this positive number, the distance. That times mg should give you the work done, right? So work done by gravity in this case, that would be simply mg times yi minus yf. And if you rearrange the terms here, you could write it as negative mg y final minus mg y initial. And the reason I made this change is, well, in physics we are interested in changes, and those differences are final minus initial, not initial minus final. So that's why I pulled out negative there. So if I define a quantity, which I call U or UG, if I name this mgy as U, I'm going to call this potential energy, then the work done by gravity is negative U final minus U initial, or negative delta U. And that's very common, very customary to express the work done in terms of the negative of the change in the potential energy, especially when the forces that are involved are conservative forces. Okay, so you associate conservative forces with some potential energy, and that's something you already know from mechanics, from physics 1. Now we're going to take this idea and apply it to electricity and magnetism, specifically electric field, electric force, and so on. So you could be analyzing the motion of a particle, a charge, a test charge. So there is an existing electric field, and then you drop a charge. Now, in general, you can calculate the work done by any force if the particle follows a certain path. All right, so I mean, this was a special case what I just showed you, but in general, you may have a particle following an arbitrary path from point A to point B, right? From A to point B. Let's say the object is somewhere here. At that instant, there's a force acting on it, and the force is pointing this way. Okay, so if I ask you, what is the work done by this force? Let's call it WF, when the object is going from A to B, following this path. How would you find that? Okay, I mean, in the previous case, it was simply a multiplication, and I assumed that the force was a constant, and the path was a straight line, and the displacement and the force were parallel, and so on. But in general, you don't have that restriction, right? But still, you have a formula to find the work done by that force. You just need to evaluate this integral, which is in the integrand, you have the scalar product of this force with dl. So dl is a vector along the path. It's a differential displacement or infinitesimal displacement along the path. So right now, dl points this way. Later, dl will be pointing that way. In the beginning, dl was pointing this way. Imagine a tangent to the path. That's where dl points at. And it's very small, okay? Of course, I exaggerated here. And f may depend on the path or may not, or may depend on the location, both direction-wise and magnitude-wise. Doesn't matter, it's a general formula. So what you do is you integrate this from point A to point B, and that's how you get your work done by F along that path. Now I mentioned the conservative forces since I was doing gravity 5 minutes ago. Yes, gravity is a conservative force, and for conservative forces, this work done by F does not depend on the path chosen. Okay, so from A to B, you could pick a different path, such as this one, and that would have no effect on W work if F is conservative. Okay. Another way to explain conservative forces is to look at loops. If the path is a closed path, like this, come back to the original point, something like this. All right, you start here and come back there. Then the work will be equal to 0 if F is conservative. All right, and if you recall from mechanics, energy, there's a relationship between F and this U, the potential energy. So to go to work therefore U from F, you integrate. What's the opposite direction? You take derivatives, right? So thinking in 3D, you basically take the gradient of the potential function with a negative sign. Of course, this becomes a vector when you take the gradient of a scalar. All right, so the gradient operator is in Cartesian coordinates, for instance, I hat del by del x, j hat, the y derivative, and then the z derivative. All right, so anyway, so that's for conservative forces. Now, let's do this. Let's apply this idea to electric fields and therefore forces, electric forces, and see what we get. All right. So it all depends on this integral here. It all comes down to this dot product, anyways, which is actually, if you consider the angle here, call it theta, then F dot dl will be F dl cosine theta, right? So if you can find a way to calculate this integral easily, do it. In some problems, for instance, a pendulum swinging, okay? The path is an arc, part of a circle, and that integral is a simple trigonometric integral, which you can do. I mean, it doesn't have to be really complicated. So let's assume an electric field. Now, I'm going to move this up a little bit. So let's say we have an electric field, some arbitrary electric field that changes, you know, as a function of the spatial variable, right? This is the electric field. And my object, which is a charge, right, is moving along this path from A to B. All right. So why do we have this electric field? Well, we don't know. Maybe there are charges, you know, here and there. Maybe a positive charges in the bottom and then a negative charge in the top. That's why we have that field. Doesn't matter because we know what the force will be given a charge and an external field. It's just Q times E. So my charge is, let's say, right here. This is the charge. Let this be a positive charge. Then the electric field and the force will be in the same direction, right? So right here, the field points this way. Therefore, the electric force is also pointing in the same direction, and dl this way with some angle, all right? So exactly same way we're going to calculate the work done by the electric force on this charge. So I'm just going to call it W, this integral from A to B. Now I need F dot dl, right? So F is Q, Q E dot dl will be the work done by F along the path from A to B. Okay, so that's just an integral. Now, I want to consider a simple example now. I'm going to put some constraints on this and see how you can apply it, all right? So let the field be a uniform field. Uniform. So the direction and the magnitude is a constant, doesn't change. So we end up with parallel electric field lines. Okay, and these are in the vertical direction. So E can be written as some constant, E0, let's say, K hat. That's the Z direction, right? Okay, that's pretty much the only restriction I'm gonna have. I'm gonna pick an arbitrary path again. So I'm gonna go from A to B like this. All right, so the coordinates, oh, well, I could do it in 3D or 2D. I don't lose anything if I just do it in 2D because I'm using the board, you know, it's a 2D environment, but it can easily be generalized to 3D as well. So this is my Y coordinate, and this will be my X. Okay, but the electric field doesn't have any X component, or I'm sorry, I think I already called this K hat, so this must be Z. I apologize. So let's make this Z. All right. So the electric field doesn't have any horizontal component. So you'll see that this X actually will not matter at all. But let's mark the points A and B on the Z-axis. Okay, this is ZA, whatever that coordinate is. And this will be ZB. All right. So as my charge moves, the vector dl has to remain tangent to that path. So it's changing its direction. All right. And that integral, if you want to do it directly, meaning you have to know every angle at every point, it may not be very easy. I mean, you know that your force will be upward if the charge is positive, yes, but what about the direction? Okay, unless you know the form of the path, the function, you know, analytically, it would be not easy just if you're given a path, an arbitrary path like this. In principle, though, there's an easy way to get the job done. Okay, so what if I move only right and up? Okay, so don't move in this curvy manner. Imagine you can only move right or left or up and down. Okay, so let's start from point A. I'm going to use green. I start right there. Okay, now the path wants to go this way, right? But I'm not allowed to go at 50-degree angle or whatever that angle is. I can either move right or up. Let's go up. Just a little step, this much, okay? And I immediately realize that it's diverging. I mean, I should be over there, but now I'm to the left of the path. So to catch up with it, now I move to the right. Remember, I can only move horizontally and vertically, step by step. So I move to the right, and then I cross the blue line. Now I'm too much on the right-hand side. I decide to go up again. I want to stay close to the actual path. I keep going up. I pass it. Now I say, hey, I should go to the right. I do that, and then up, right, okay? If these steps are really small, I'm in good shape, okay? Smaller the steps, better the approximation to the actual motion here. So it's probably a long right walk, and then right again, and up, right, up, right, up, right, up, right, up. Probably I'll end up at point B if I keep doing this carefully. So what changed? Well, now I can do the integral very easy, because I know that the dl, whenever I move horizontally, dl is perpendicular to the electric field. But whenever I'm moving up, dl is parallel to the electric field, or to the force for that matter. So these little increments, okay, let's say when I'm going from here to there, okay, this much, this little increment there, let's call this zi. As long as I'm moving up for zi, a distance of zi, I remain parallel to the electric field. Therefore, only from this contribution, the integral is nothing but the force, which is my test charge. Okay, my charge was Q, right? So Q times the electric field. So that is the force. Force times distance. That is the work done by the electric field. Zi, okay? But whenever I move in the horizontal direction, so if I go from here to there, let's say, so that would be xi. The integral will be 0 for all x's like this. For z's, I simply multiply the up movement by the force. So consider all these up motions, okay? 1, 2, 3, 4, 5, 6. You may have as many as you want if you prefer small increments. If you line them up, if you add them up, what do you get? you get this. Keep doing for all I, you get pretty much QE times this length. That is ZB minus ZA. Okay, so that is the work done by this electric field, therefore the force. Okay, so it looks very similar to the object moving under the influence of gravity, right? Free fall. So let's do the same trick even. We can do work equals negative delta U, right? So if you rearrange this as negative Q E0 ZB minus negative Q E0 ZA. Okay, so negative Q E0 Z. Now, why did you get a negative number? Now, the test charge was positive, right? So this force was already pushing it upward. Okay, so that force would do a positive work. That's fine. This is a positive number anyways. ZB minus ZA is a positive number. So negative UB minus UA would be equal to work. And the path does not really matter. You could simply take this path here, and then you would end up with the same amount of travel in the z direction. So that wouldn't make any difference. So let's consider a couple of cases. First of all, how can we have these uniform field lines? We can use parallel plates charged with opposite charges. And you can do this with a battery. We're going to see these in detail when we do capacitors. Okay, so you can charge this positively and this one negatively. Therefore, you have this uniform electric field between the two charged plates, at least in the center. Over there, they start curving up like this. Okay, but we remain in the middle, so the field lines are pretty much uniform. And since this path does not really matter, let's just move in a vertical way. Okay, so if you move, and the separation between the two plates is, let's say, D, and then we're going to move from here all the way up to the other plate. Okay, so the options, we can move up or down. Another option is we could use a positive charge or a negative charge. So option one, move up, and the charge is a positive charge here. So if the charge is positive, the force on the charge is up. F points upward. The displacement is simply d. So this F times d is work, right? So positive charge. So multiply this charge by the electric field. That gives you the force, F, and multiply F by distance. This will give you the work done. I mean, if you want, you could use your z coordinate again, like you did. This would be z equals 0, and this is z, what did we call it? A, right? And this one, zb. So d is nothing but zb minus za, right? So work done by the electric field is q e times zb minus za. So if we do that, it's just like the previous case. What happens to the potential energy, U? Electric potential energy. Does it increase or decrease? Okay, look at the equation right there. Does it increase or decrease? Okay, it decreases, right? U decreases as the particle moves up. Now, what if you move downward? Move down. Same charge. Now you're here, but you're going to move downward. Well, the force is still up, remember? The force did not change direction. Force only depends on what the charge is, and if the charge is positive, it's still pointing upward. Now you have to do the positive work, and the charge will be on the passive side. The electric field or the force would do negative work, all right? So work will be equal to negative QED or negative QE ZB minus ZA. All right, so in other words, this will be equal to the final point is here, right? This is the initial, this is the final for this game. So you would have final is ZA. You would have Q E ZA with a negative here minus Q E ZB. Okay, this is final. This is initial. So what happens? U increases. U increases. All right. So the other two options are move up and down again, but take a negative charge. All right. So what if your charge is negative? If the charge is negative, the force is downward. Okay, this charge wants to stay there. If you want to bring it to close to the negatively charged plate, you have to do extra work, right? You have to do the positive work. So the work done by the electric field would be negative. And if you start from top, and then go down, the force is downward, then the work done would be positive, of course. So let's list those as well. 3, move up with a negative charge. If you move up with a negative charge, you're actually increasing the potential. And if you move down with a negative charge, the potential is decreasing. All right, so whenever you're doing something that increases the electric potential energy, it is actually you who is doing the positive work, right? And if the charge wants to go in that direction under the influence of the electric field, then that force is doing the work, and the potential energy will go down. All right, so that is the idea behind electric potential energy. Now let's apply it to a even simpler case, like 2-point charges. All right, so let me scroll this downward. Let's take a point charge here. Point charge Q. Now I know that it's going to create an electric field which is radially outward in all directions. But now I have a second charge, let's call it Q prime, and let it be also a positive charge. And it's here right there. A positive, a test charge, if you will. And initially it is RA away from the first charge. This is point A. And it's going to move along this path to point B. All right. So that will be RB away from the first charge. Now I know that the electric field can be easily found using 1 over 4 pi epsilon 0 Q over R squared, right? It's radially outward. I can write it as a vector by putting this hat on R. That's the unit vector. So the force then is equal to this field times Q prime. That's the force on Q prime, right? So let's show the force. Force will be in this direction. Now the force is obviously a function of R. All right, it changes. So when the force changes, we can't simply multiply the force by the distance, like RB minus RA, okay? We have to do the integral the right way. So the work done by this field, electric force from A to B, you have to do that integral from RA to RB, then write your force, that is 1 over 4 pi epsilon 0 Q over R squared. Now, remember, this is actually the integral of E dot dl, and dl along that direction is nothing but dr, all right? So we have two vectors. This guy here, which is ER, and we have dl, which is nothing but dr r hat. If I take the dot product of this with that, what do I get? I get EDR, okay? So I have the electric field here times the force, Q prime, times dr. All right, so that's the integral. And this integral is Easy, right? This gives you negative q prime times q divided by 4 pi epsilon 0 1 over r. And the limits are RA to RB. All right. So that will be equal to, now here's what I'm going to do. I'm going to factor a negative here and also q prime. And you'll see why I'm going to do that in a minute. So what is left here? In the first term, I have 1 over 4 pi epsilon 0 q over RB, and then minus, remember I factored the first minus out, so this is minus here, 1 over 4 pi epsilon 0 q over RA. Okay, so I'm going to call this guy U now. This is U at B, and this will be U at A, so that I simply have negative Q prime. I'm going to call it UB over Q prime, sorry. UA over Q prime. And then this becomes negative delta U, with U being Q prime over 4 pi epsilon 0 R. All right, so why did I factor that Q prime? Because I'm going to define a new quantity called electric potential. Electric potential. And I'm going to treat Q prime as a test charge, which was the idea from the beginning. So V is the letter I'm going to use. V will be this U over Q prime. Okay, so that my physical quantity here is independent of Q prime. All right, so it's a property of the space because of the source, of course. If the source changes, the potential at that point will change as well. So V of R, or V at R, because of the source, is 1 over 4 pi epsilon source charge divided by R. Okay, for point charges, this will be my electric potential. Now, the idea is you need a reference where this potential will be 0. So take R to infinity, for instance. 1 over R goes to 0. So at infinity, this potential will be 0 in this picture, okay? So you may have some situation where infinity doesn't do the job. You can pick another point to be your reference point where V is 0. Okay, that's fine. So this will be our electric potential, and energy is measured in joules. So U is still in joules. Work is in joules. But now we're dividing it by charge. So joules per coulomb, okay, that kind of unit. So we're going to call this a volt, 1 volt. Okay, this V means volts. Now, if you apply this formalism to the force formula, so here's what I mean. So we had F dot dl from A to B. This was equal to work done by this force from A to B, right? So what I did was I separated the test charge from the field. So from here, I go to A to B. E dot dl. Okay, so this was work equal to test charge times E times dl, or E dot dl. And we just saw that this was equal to negative Q prime VB minus VA. Okay, so you can get rid of the Q primes and write this as negative VB minus VA equal to this integral, or distribute that negative to what's inside the parentheses and write it as VA minus VB in alternate form is equal to from A to B E dot dl. Okay. So you take work and energy out of the picture. You just think in terms of electric potential, this new quantity, and the electric field itself. All right. So for instance, if you go back to the parallel plates that we considered half an hour ago, right? Two plates with positive and negative charges, which were separated by a distance d. Now for this setting, the electric field was uniform, a constant electric field. I picked this example because the integral is really simple in this case. It just becomes E times d. So this integral is nothing but E times d. All right? I'm moving from A to B. And when I'm doing that, the potential energy is decreasing. Therefore, I'm going from a high potential to a lower potential. So VA is greater than VB. And the difference is delta V, right? So here's a very simple formula that relates the potential difference to the electric field. Okay, so I brought this up because I wanted to mention another unit for or equivalence of the volts. Here it was joules per coulomb. In this case, you can call it, okay, so you have the electric field, and what was the unit for electric field? Newtons per coulombs, right? From F equals QE, you had the unit as newtons per coulombs. So 1 volt is equal to 1 newtons per coulombs times meters. Or the unit for electric field would be volts per meters, or unit of E will be volts per meters. All right, so that much about the units. What if we have, okay, so if you take a look at what I did here, over here, this is nothing but the electric potential energy, right? Now you can interpret it this way. I mean, that's the energy when you have two charges held apart at a distance r. The interpretation is this will be the work Suppose these two are both positive charges. This would be the work you would do to bring the second particle, or the first, doesn't matter, one of them, all the way from infinity to where it is. All right? If one is positive and the other one is negative, they want to get closer because the force is attractive. Then the work you would do to separate them, so take one of the particle and carry it away all the way to infinity. The amount of work you would do would be equal to this expression here, okay? That's how you interpret it. So now you ask, okay, what if I have more than 2 charges? What if I have 3, right? What if I have 3 charges? Q1, Q2, and Q3. Suppose you have these two, Q1 and Q2. So you already had this potential energy of 1 over 4 pi epsilon 0 Q1, Q2 over some R. Okay, let this be R. Okay, that would be the energy. But now you're introducing a new charge to the system. You're doing some work. So if you pin those 3 where they are, means I need another distance here. Call it R prime. And the distance between Q2 and Q3 is R tilde or something. All right. Then I have to add more terms to this energy. All right. Plus 1 over 4 pi epsilon. Now consider Q2 and Q3 divided by R prime. And also add to this Q1 and Q3. The distance is R prime. Okay, you keep adding, you keep adding and consider all pairs available. This will give you the total energy of the system. Now what is left? Let's find electric potential for a given charge distribution. Okay. Before I do that, let me say one more thing about the unit system here. Since now you multiply the potential by the charge to get the potential energy, there's now a new unit for energy. Unit for energy. Besides joules and even calories, if you go that way. So you take a unit charge, which is an electron. Now, the electron has a charge equal to 1.6 times 10 to the negative 19 coulombs. You take that negative charge, or electron, and move it across a potential difference equal to 1 volt. All right? So you move it from A to B, but the difference is equal to 1 volt. This energy, this work, or this change in potential energy, okay, is called 1 electron volt. This is the new unit, 1 electron volt, EV. All right, sometimes you will hear on the news, this new accelerator, you know, accelerates particles to such and such mega electron volts, giga electron volts. That's what it is. It's a form of, it's a unit of energy. So 1 electron volt in that sense, since Q times V is equal to U, right? You just multiply the charge by 1. This means that's equal to 1.6 times 10 to the negative 19th power joules, all right? That's the unit of, that's how you define 1 electron volt. Okay, so I'm going to stop here, and in the second video, I'm going to do some calculations, like some charge distributions, and how you calculate the electric potential for a given charge distribution. And I'll be pretty much done after that. Okay, so, and maybe I'm gonna apply that gradient I showed you earlier, this equation, gradient of V, negative gradient of V is equal to, I think what I showed you was this, gradient of U will be equal to force, negative gradient. Okay, so if you just divide it by Q, you'll get that, right? So I'm going to show you this gradient. This operator is also called a nabla. Nabla. Because it looks like some ancient Egyptian instrument that looks like this, you know. So you say nabla. Nabla V means the gradient of V. Okay, all right, so I'm going to stop here and then do the rest in the second video. Here, let me stop.